is the title of my talk, and I've designed this talk as like a general overview. So let me start by mentioning what I mean by diffusive phenomena. So diffusion, it really refers to this natural trend towards equilibrium, balance or spreading of quantities in physical systems. And this is a very natural phenomenon that we observe in nature, for instance, in thermodynamics, theory of elasticity, in economics and social behavior, math, biology, chemistry, probability, imaging processes. And it's a very powerful mathematical tool as well to study problems in geometry and things like that. So when you have this idea of diffusion, that diffusion is this natural trend towards equilibrium, a natural question is what kind of mathematics evolve out of this? So if you have a problem that has been designed to model diffusion, what kind of equation, what kind of PDE are you expect to find? So to answer this question in a didactical way, let me pose a question. So imagine that we want to find a function. This is a question that you can put your Calculus 3 students. You want to find a function that's called h of x that has the property that the value of this function at every point y equals its own average. Okay, so of course it's very related to this idea, this intuitive idea of diffusion that I mentioned before. If you describe it mathematically, that's what is written. So you want the function h to have this very nice property that the value at a point equals its own average at all scales. Okay, and it's a simple exercise to verify that as long as the function has enough smoothness, if you assume that the function has enough smoothness, then this is actually equivalent to the function satisfy the Laplace equation, right? So the second derivatives, the sum of the pure second derivatives equals 0 is equivalent to this nice averaging property. And the Laplacian is, of course, the prototype of a second order elliptic equation. It's a very homogeneous, constant coefficient. It's the nicest second order operator that we have. Okay, so what I'm trying to convey here is that if you have a model that involves some sort of diffusion in that sense that I mentioned before, then the kind of PDE that will drive the system will be of this elliptic form. Okay. And one of the key features of the diffusion processes are regularity. Okay, so whenever you have diffusion process, you have this idea of balance and spreading. And of course, if you think about things that spread and balances out, some sort of regularity should surface. And to understand this diagram is a major scientific endeavor that has to do with regularity theory. Okay, is to understand how these all physical processes are connected with regularity theory. So in a way, regularity theory is really the very mathematical manifestation of the diffusion mechanism. So somehow diffusion happens in the physical side of the phenomenon, and what we see as mathematicians when we are studying the model is the regularity theory that appears. But for today, what I'd like to do is I'm going to reverse these implications and to say that conversely, if you have a PDE that has some sort of smoothing defect, and I'll try to explain what I mean by that, this should reflect on some diffusion deficiency, okay? And to understand this connection in a quantitative way is a critical mathematical endeavor. And typically there are two ways of understanding a diffusion deficiency. One is when your system is modeled in composite material, okay? So maybe the roughness of the material will imply some laws of regularity. And, and another way of losing regularity is because the system that you're modeling is really nonlinear, and nonlinearity causes the system to drop regularity. And I will try to explain both cases and what are the implications of both cases. But before I do so, let me explain what I mean by diffusion in composite materials, and this is very important in material sciences. So if you are studying a problem where every direction is equally good, then you should expect the operator that models a problem like this to be homogeneous, which is related to the spherical symmetry that I explained before, that is connected with the Laplacian, right? So if I assume that I have a homogeneous material, there is no preferable direction, and everything is smooth, and there is no obstructions for the diffusion to flow, then you should expect that the problem is modeled by the Laplacian. So the Laplacian would be a very good approximation for this system. However, if I'm in a heterogeneous medium where there are preferable directions and the medium is made of composite materials, so maybe there are directions which are better than others, and mathematically, to be able to describe that, you introduce coefficients, these matrices Aij of x, which are matrices that change point by point. And what these matrices does in the system or in the model is the tangible properties of the material. It's going to tell me how easy it is to flow in one direction in comparison to the others. Okay, and as long as this is a positive matrix, you are still dealing with a diffusion processes, and therefore the operator is elliptic. Okay, is elliptic in the sense that it's really modeling a diffusion process. But I want to make the argument that if you are in composite materials, is a sort of an diffusion ceasing. You do have diffusion ceasing, which is a manifestation of laws of regularity. Of course, the regularity of the solution will have to do with the regularity of the coefficients. But in some way, and this is what I'd like to convince you, is that this is an artificial diffusion ceasing. And there are implications insofar as regularity theory is concerned. So to give you an example, imagine that this is your living room, and you have like a cooler with your juice. And what you're going to do is you're going to place your cooler conveniently close to you, right? So you are changing the system based on your own convenience. Okay, so if I want to understand how how heat will or the temperature distribution in the room will adjust itself, you will have this Aij of x here has to do with the materials that comprises the living room. Okay, f of x here is a source function. Maybe you have some heat, or maybe you have another system of either pumping heat inside or removing heat inside. And if your cooler is good enough, what you expect is the temperature inside of the cooler will be constant. Let's say 0 Celsius. But because you pick the cooler and put it close to you, and that was your decision, not the system decision, you should not expect much regularity of the temperature around the cooler. because the system had no say on where the cooler should be. Okay, and this is what I mean by an artificial diffusion ceasing. If there is diffusion ceasing, this is you can see this by understanding the regularity of solution of the solution of the temperature around the cooler, but in some way is artificial, and that's why the regularity drops so much. So solutions will just be, let's say, in general, Hilder continuous. Whereas in a nonlinear phenomenon, and I'm going to explain this, is a sort of an intrinsic or intelligent diffusion ceasing. It's still, there are some diffusion ceasing, but it's much more intelligent. And I will explain this with another system. Instead of having a cooler, imagine that you have a thermostat that adjusts the temperature in the room. So basically what you have is a distribution of temperature, let's say phi, inside of the living room that you'd like to heat the system or heat the living room as to keep this temperature distribution. In general, we always are led to think of a constant temperature distribution so far as thermostats are concerned, but it doesn't have to be. But in this case, what happens is that you will still have an elliptic operator acting on the living room, which may or may not be linear. That's not the point. So this AIJ has to do with the furnitures of the room. But now the main difference is that now the temperature will be equal to phi whenever needed. Whenever needed. So here you see that there is some diffusion ceasing because the thermostat will interact with the temperature as to keep the minimal temperature at control, but it will do that in an intelligent fashion. So the temperature will interact with the system. It will decide what's the best way of putting heat. Okay. So I would like to point out that even though the system seems to be driven by a linear operator, which is this one divergence of Aij of x gradient of the temperature, but when I describe the problem like this is really a nonlinear problem, because where the diffusion occurs depends on the temperature itself. It depends on the prospective solution of this problem. So even though it seems to be a linear problem, this is a nonlinear phenomenon that is driving the temperature distribution. So the mechanism ruling the temperature interacts with the medium, and therefore a higher regularity is expected on these, let's say, on this boundary of where the temperature needs to be adjusted in comparison with the cooling problem. Okay, so let me explain two models of nonlinear diffusion. The first one is one that appeared yesterday on Professor Urbano's talk, is the P-Laplacian. So let me explain the P-Laplacian in a didactical fashion. So the P-Laplacian appears in the calculus of variation. You minimize the P-Dirichlet integral. You may or may not have a forcing term f of x. And sorry, could you say that again? And it's a very easy exercise to see that minimizers, well, they exist by convexity, and minimizers of the energy functional satisfy what is called the P-Laplacian equation. So divergence of the gradient of u to the power p minus 2 gradient of u equals f of x. And again, if you don't like f of x, think of this to be 0. So the key feature of this is a nonlinear operator, and but the key feature of this system is because the coefficients, the gradient of u to the power p minus 2, I'm thinking of p greater than 2, they generate at critical points. So there is a clear diffusion ceasing at critical points. Here are the known facts about the P-Laplacian. So if you think about the p-harmonic functions, so if you want to develop like existence theory, a uniqueness, all these soft analysis quote marks, it's very similar to the linear theory. And I'm not saying that they are easy to be proven, but they're certainly very similar. So the techniques that are used to prove these kind of results for the Laplacian often can be used to prove the same kind of results for the Laplacian. There is also a robust nonlinear potential theory that evolved out of the study of these kind of operators. And it's been known for, what, 60 years that solutions are C1 out. So here you see there is diffusion ceasing because solutions are not real analytic as in the case of the Laplacian. So the regularity drops from being, let's say, infinity to just being C1 alpha. And this, as I said before, this is a mathematical manifestation of diffusion ceasing. There is a fading on the diffusion attributes of the operator, right? And the goal here is to understand how and why, okay? And of course, I could just say that the coefficients of the operator vanishes at critical point, and therefore I have laws of regularity. But if I just say this, I'm not telling you the whole story. And that's the key point that I would like to make today. And to do that, I'll make a small detour. I will be talking about free boundary problems. I'm not going to make an analogy to try to convince you that you need geometric insights pertaining to these kind of problems to be able to say things in a quantitative level as to why p-harmonic functions lose regularity. Okay, so very briefly, let me mention one of the problems. As a matter of fact, this is the problem that appeared in one of my slides back on the thermostat thing. This is called the obstacle problem. So you are interested in finding the equilibrium position of a membrane resting above a given obstacle. Okay, so it's a very typical physical problem. And even in the linear setting, you want to minimize the Dirichlet integral, let's say, for functions which are restricted to be above an obstacle. Okay. And there is a huge literature on this kind of problems. It's a very important problem that appears in applied sciences, even in economics and financial engineering and so on. So it's known that solutions of this problem are harmonic whenever U is above the obstacle. Solutions are C11, and this regularity is optimal. The word solutions are the second derivative of solutions are bounded, but they are not continuous. Okay, they are not continuous. So here you see that there is a loss of regularity, but what I'm trying to convey here is that this loss of regularity is a much more precise than the typical kind of regularity theorems that we are used to having for ordinary PDEs. Okay, so the observation that I would like to make here and the connection that I want to make between p-harmonic functions and solutions to the obstacle problem, solutions to the pre-boundary problem is the following. P-harmonic functions, as a matter of fact, p-harmonic functions are C-infinity, as a matter of fact, real analytic outside the critical points. Okay, as much as solutions to the obstacle problem are C-infinity because they solve the Laplace equation away from the obstacle. Okay, so the analogy that I'm trying to propose here is the following: is that p-harmonic functions lose regularity at the critical points as much as solutions to the pre-boundary problem do along their corresponding pre-boundaries. However, and this is critical, however, for pre-boundary problems, this is very well precised, quantified by the geometric behavior of the solution at the pre-boundary. And there is tons of technologies to be able to say how the solution behaves, solutions to free boundary problems behave at the free boundary. Okay. And this brings us to this very successful a program called non-physical free boundaries. This is a program that we have been developing in the last 10 plus years with many collaborators, including Professor Urbano, which is precisely this connection. It's a heuristic principle that makes the connection between free boundary problems and linear or nonlinear diffusion processes where you see some defect on the regularity, and you try to interpret the specific points where solutions lose regularity as being an artificial or a non-physical free boundary. So the heuristical principle is the following: the smoothing defect is in a given model indicates diffusion. That's what I've been saying since the beginning of my talk. Whenever you see a diffusion process losing regularity, something is going on there. Okay, something is going on there. It could be because the coefficients are rough, which is a different kind of problem, even though we can apply non-physical free boundary techniques to study them, or it's a nonlinear phenomenon, and then you have to understand what's going on those systems. So for robust models, and this is the nonlinear kind of problems, diffusion ceasing happens in an intelligent way. So in other words, they choose where to accommodate these fading on diffusion. Okay, it's the solution interacts with the system and chooses where, for instance, in the case of the P-Laplace equation, the solutions to the P-Laplace choose where to have their critical points as to optimize the regularity. And this comes from the very minimization problem that they solve, right? Because they're trying to minimize a P-Dirichlet integral. They will have to choose, critical points are unavoidable, but they will choose where to put those critical points in the best way possible. And that's why solutions are C1 alpha and not only just Hillary continuous. And this is, as I said before, it's been a successful program that we have put together with many collaborators, young students, and it's been very, very a delight to pursue problems with this perspective. There are a few select advanced that I brought here. Using these kind of techniques and this kind of analogy and geometric tools from free boundary problem to study nonlinear diffusion, we have been able to refine Schauder theory to obtain quantitative or qualitative regularity for problems with borderline sourcing. This is a problem. It's a nice paper that we wrote near to 10 years ago with Miguel Urbano. We have obtained a universal model of a continuity with students in Fortaleza, geometric estimates for degenerate PDEs. There is also this paper that we wrote with Damião Araújo and Miguel Urbano on the CP prime regularity conjecture. And we have done many, many other things using these kind of tools. And let me very briefly comment on the CP prime regularity conjecture, which is a problem that we are particularly proud of. So let me explain what the CP prime regularity conjecture is and what can be done using these kind of techniques to study the problem. So it's been known, as I said before, since the 60s, that solutions to the P-Laplace equation, even with a source, are locally C1 alpha. Okay, so solutions are C1 alpha. They cannot be better than C1 alpha. There are several counterexamples, but there is one specific counterexample, which is this one. If you compute the P-Laplace, this is a one-line calculation. If you compute the P-Laplacian of this radially symmetric function, the absolute value of x to the power p divided by p minus 1, you get constant. And constant, of course, is a bounded function, right? And this function is not C2 at the origin, right? It's not C2 at the origin because p divided by p minus 1 is a number greater than 1, but less than 2. Okay? So the conjecture, after much thought, and this is a conjecture since the late 60s, is that any solution to this equation should be CP prime regular. P prime here is the dual of P, which is precise this number P divided by P minus 1, which again is a number between 1 and 2. And this is the conjecture. And what this conjecture is saying is kind of counterintuitive in a way, because what this conjecture is saying is that among all possible functions whose P-Laplacian is bounded, this naive-looking radially symmetric function is the worst one. So this is as rough as it gets. All the other functions will be at least as smooth as this one. Okay, and so regarding this CP prime regularity conjecture, we don't have a full proof of this regularity conjecture yet, but using this non-physical preboundary, that's what I was trying to say. If you just say, okay, the coefficients of this operator vanishes at critical point. And this is, I mean, many authors have done that before, and you can develop a robust nonlinear potential theory. You can prove many things just using this observation, that where the critical points vanishes, you have diffusion ceasing. But if you interpret them as a non-physical pre-boundary problem, then you can advance the studies and prove much more precise solutions. And here you see that preciseness is key. You don't want to prove that solutions are C1 alpha for some alpha. You want to prove that solutions are C1 alpha star for a very specific exponent alpha star, which is p prime minus 1, right? So what we have been able to prove was that the conjecture is indeed true for functions with two variables, so in the plane. The conjecture is also true in the presence of some sort of symmetry. So if you give me a little bit of symmetry, the problem is true in any dimension. And also, if the solution is prevented from having, it can only have critical points of extreme critical points, in other words, local max or local mean, then the conjecture is also true. Okay, so basically, the only case that we were not completely able to prove the conjecture is when solutions have saddle points, so critical points of the saddle type. And this has to do with, this is the kind of critical points that appear for p-harmonic functions. P-harmonic functions cannot have local max or local mean because of the maximum principle. So we believe that there is an obstruction that comes from this kind of thing, because this is the kind of in other words, at least heuristically, if we were able to prove the CP prime regularity conjecture for in saddle points, then at least heuristically, we should be able to apply this to p-harmonic functions. And understanding sharp regularity for p-harmonic functions is a very complicated problem, very complicated problems. Even in 2D, the expression is very complicated. Okay, so let me go a little bit fast. How am I doing with time?
You have a few more minutes.
Okay, so let me just mention very briefly the other kind of problem, which is the non-variational theory. It's the theory of fully nonlinear diffusion processes. So this is a nonlinear, it's a non-variational theory that has to do with fully nonlinear operators. And again, you see a diffusion, a loss of regularity. Solutions are just C1 alpha. It's a completely different theory, but nonetheless, it bears a diffusion process in it. So here's a much more complicated, because you don't have any clear relation as to how solutions are losing regularity, right? And in fact, solutions are just C1 alpha, and this alpha that comes from Caffarelli's theorem actually can degenerate. And this is a program put together by Nandrashvili and Valadou. And another important result due to Caffarelli in the late 80s is that solutions, under the hypothesis that f harmonic functions, in other words, solutions that satisfies f of d squared of h equals 0, is a classical C2, then you can develop a W2P theory. So solutions that satisfies the equation being equal to a LP function are in W2P. Okay. So one way to reinterpret the W2P regularity theory of Caffarelli is saying the following, is that if the diffusion agent F is efficient enough, then you have this duality. If you have a function that satisfies f of d squared of u is a LP function, then this is equivalent, because of W2P, the potential theory for the Laplacian, is equivalent to saying that the Laplacian of u is in LP. So the idea we had, it's a recent result, is that if f is a fully nonlinear operator, because it's a diffusion system, we should be able to try to compare its performance with a weaker model of diffusion. So maybe fully nonlinear are not like, it doesn't fully diffuse as the Laplacian, but maybe you can obtain a slightly less ambitious result. And this is a result that I'm very happy to report. This was proven with Edgar Pimentel, which is former student of Diogo Gomes, and Maxo Santos, which is a student that was co-advised by me and Edgar, that says that if you have a function, now f is genetic, a genetic fully nonlinear operator, whose f of d squared of u being in LP, this implies that a fractional diffusion process of u is in LP. And as a corollary, you can obtain a W1 plus SP estimate, which is now is a universal thing. So basically what we're saying is that if you may not have W2P estimates, but because you can compare with a fractional operator, you still have some increased differentiability of solutions. And I think this is a great place for me to stop, and I appreciate your attention. Thank you.
Thank you very much for this very nice talk. And I guess it's time for some questions. Please feel free to ask questions. We would love to have some questions from the audience. Okay, perhaps I may start with one. It's more on the curiosity side. You made some parallelism with these composite materials, and composite materials have been widely used in engineering, and they are very successful. And do you know of real world applications of these diffusion things that somehow perform better than composite materials?
Exactly. So it's a very, very fortunate question, because I should say that those results, even though they sound like a very theoretical mathematical results just for the delight of mathematicians, they are actually very applied problems. So understanding, let's say in the case of the P-Laplacian, understanding very precisely how the P-Laplacian smooth out functions is critical in applications, because there are many cases where it's not that you want solutions to regularize very fast. You'd like to be able to fine-tune how the diffusion acts on the solution. For instance, this is a case when you want to treat images. So in imaging enhancement, what you would like to be able to do is to adjust the diffusion point by point. And by knowing how much each diffusion process will act on the solution, you have a better precision. For composite materials, it's the same. So for instance, this appears in homogenization processes. So for instance, if I look in a metal alloy, maybe if I look in a microscopic way, there is a very rough composite material. But if I look in a macroscopic distance, I could kind of think that this is a homogenized material. And to be able to understand how things change from one scale to another is important when you are designing these kind of materials. So this has to do with the George estimates or Krylov-Safanov estimates, depending on what kind of operator you are using, and the homogenization process that appears when you go from the microscopic level to the macroscopic level. And basically, if you're not interested in understanding things that happens like in the microscopic level, you want to have a more like macroscopic level, you can apply that because of regularity estimates. And to be able to say that things go from one scale to another is also very important in applications.
Thank you.
Rita, can I ask a question?
Sure, please, by all means.
So, Eduardo, this program has been very successful, this program of applying this idea of artificial free boundaries to the regularity of nonlinear equations, but some PDEs remain very strongly resistant to this approach. For example, the infinity Laplace equation. Can you comment on that? And
yes, for the infinite Laplacian equation, it's true that, I mean, we have been able to study free boundary problems governed by the infinite Laplacian. But one thing that I truly believe that could be a possibility is, because you see, infinite harmonic functions, and this is an important question that Miguel Urbano is bringing here, this is an important operator that has to do with the best Lipschitz extension problem. It is also connected with many applications, recent applications in machine learning and so on and so forth. What happens is that the infinite Laplacian can be understood as a limiting case of the P-Laplacian. So maybe we cannot apply directly those techniques to the infinite Laplacian, but maybe if by understanding quantitative estimates for the P-Laplacian, maybe not the optimal ones, but maybe we can obtain C1 alpha estimates for some alpha that depends on P, which may not be the best one, but the estimate does not degenerate as P increases. Maybe there is a hope, and this is my hope, that you will arrive at the infinite Laplacian with some C1 alpha regularity left. So you may lose through the process, but as long as your estimates, quantitative estimate, if I just say that solutions of the P-Laplacian equation is C1 alpha for some alpha, then I lose the information. But if I have quantitative estimates, and these quantitative estimates do not degenerate as P go to infinity, this could be an approach to obtain a differentiability in the C1 alpha level of the infinite Laplacian. So let's keep the high hopes that this one day will succeed.
Yeah, we have to do it at some point.
Yeah.